At Deep Green Capital, we are willing to say what others will not. The AI and quantum computing revolution has rewritten the energy equation. Data center demand alone could reach 945 terawatt hours a year by 2030, more than Japan generates today. At the same time, renewable deployment is hitting hard limits in grid stability, critical minerals, and physical infrastructure. Net zero by 2050 remains essential, but pursuing it through renewables alone while scaling AI infrastructure is not just difficult, it is impossible. The math does not work, the physics does not work, and the timeline does not work. A credible energy strategy requires an honest admission. Natural gas is not a fallback, it is the foundation of this transition. A lower carbon fuel with existing infrastructure that can both power the computational revolution and stabilize grids as we build the renewable future. The artificial intelligence revolution has created an energy demand curve with no historical precedent. Unlike past technology shifts that unfolded over decades, AI infrastructure is scaling on a timeline measured in years. Today, data centers supporting generative AI and machine learning consume around 130 terawatt hours of electricity annually as of 2025. Research from Goldman Sachs and other modeling bodies projects a 165% increase in data center power demand by 2030, pushing total consumption toward approximately 846 terawatt hours a year. This exponential growth collides with real-world capacity constraints across generation, grids, and supply chains. Meeting it will require a diversified energy mix, with natural gas playing a critical role alongside renewables to keep pace with AI-driven demand during the transition. Climate policy calls for rapid scaling of renewables to meet net zero 2050 goals. But the engineering and grid data expose hard constraints that policy debate often understates. Grid intermittency and stability are not side issues, they are structural. Existing power systems were built around centralized baseload generation and dispersed demand, while renewable output is intermittently distributed at the very moment demand is becoming more concentrated in data centers that require constant computational throughput. As data center demand grows by at least 165% over the next 5 to 6 years, peak loads will hit unprecedented levels precisely when renewable generation is offline or insufficient. Critical mineral supply chains present an additional bottleneck that the renewable energy acceleration narrative inadequately addresses. The shift to renewable energy creates acute dependencies on lithium, cobalt, nickel, and rare earth elements, concentrated in specific geographies with complex supply chain vulnerabilities. The Global South controls roughly 70% of lithium production, 60% of cobalt reserves, and holds near monopolies on rare earth processing. Supply chain disruptions or from mining bottlenecks translate directly into delayed renewable deployment. McKinsey and the Energy Transitions Commission estimate that the net zero energy transition requires $275 trillion in capital spending through 2050, equivalent to $9.2 trillion annually, or a $3.5 trillion annual increase above current investment levels. This represents capital reallocation at a scale without historical precedent. Renewable deployment will necessarily proceed at constrained pace. The physics and engineering of scaling wind and solar cannot be accelerated beyond certain physical limits, regardless of capital commitment. Let me please make this essential point. We acknowledge that climate change is real and serious. But acknowledging this does not justify adopting energy policies that are financially unsustainable or technically infeasible. Now, let's consider natural gas. Natural gas holds a crucial, often discounted role in any realistic energy transition. With approximately 36.5 megajoules per cubic meter, its energy density and ease of storage and transport remain fundamentally superior to electrochemical storage at current development stages. For data centers requiring sustained 125 kilowatts per cabinet, with cooling demands adding another 40% to total electricity consumption. There is still no proven renewable-only solution for reliable 24/7 power at scale. While natural gas generation can ramp within minutes to provide the frequency regulation and voltage stability that make large-scale renewable integration possible, energy transitions reshape geopolitical power structures. The shift from coal to oil in the early 20th century concentrated geopolitical power in petrostates. A renewable energy transition creates different vulnerabilities, dependencies on specific minerals concentrated in specific nations, with supply chains vulnerable to disruption. China controls approximately 70% of global battery processing capacity, a concentration more acute than OPEC's historical oil leverage. Energy security must be reframed around reliable renewable supply, secure critical mineral chains, and resilient power infrastructure that can withstand geopolitical shocks. Natural gas, produced across diverse geographies with more decentralized supply chains than many renewable minerals, will strengthen security by reducing concentration risk. While the net zero transition still implies additional spending of multiple trillions annually above current investment levels in developed economies for the next 25 to 30 years. The computational revolution isn't just happening alongside the energy transition, it could fundamentally transform it. AI has the potential to accelerate renewable energy deployment and optimize how our electrical grids operate. Take cooling efficiency in data centers, for instance. Google's work with DeepMind has already shown how AI-driven algorithms can significantly reduce cooling energy needs. Beyond that, AI can speed up materials science research, helping us develop better batteries and more efficient solar panels. To unlock these benefits, we have to get the sequencing right. We cannot use AI to optimize renewable deployment if energy constraints prevent us from building AI infrastructure in the first place. The practical path is to build computational capacity first, using the most reliable energy sources available, including natural gas, then apply that capacity to solving the complex optimization challenges of the renewable transition. Quantum computing may eventually deliver exponential gains with modest energy use, but it is not yet production ready for grid management. So classical AI systems will need to operate at scale alongside quantum development well into the 2030s and beyond. The inescapable truth is this: something must yield. We face a fundamental choice. Either we extend our decarbonization horizon to 2080, abandoning the 2050 target while still pursuing renewables with urgency, or we acknowledge an unpopular reality: natural gas isn't optional. It's the foundation upon which we'll build the AI infrastructure that ultimately unlocks our energy future. The second path isn't just realistic, it's the only path forward. Nations that embrace pragmatic energy policy, that treat natural gas as the bridge while simultaneously driving renewable and quantum computing innovation, will do more than attract capital and secure reliable power. They will achieve what their idealistic counterparts cannot: actual decarbonization. The reality is we can't pursue unlimited AI deployment while hitting 2050 net zero with renewables alone. Honest climate advocacy requires honest energy policy, and that means acknowledging natural gas as an essential bridge infrastructure for the decades ahead. The sequencing matters. Build the computational infrastructure using the most reliable energy sources available, including natural gas, and then use that computational capacity to solve the increasingly complex optimization problems of the renewable energy transition. For more information, please look up deepgreen.capital. Thank you for listening, and bye for now.